So we continue looking at this special publication network of things. So this document actually considers 5 primitives that exist in a network of things. We talk about the first two, namely sensors and aggregators. And this also considers that aggregators have two actors, uh, clusters and weight. So in our previous two videos, we mentioned this. Now we are continue looking at the remaining primitives. The third one is communication channel. A communication channel is a medium by which data is transmitted. For example, physical via USB, wireless, wired, verbal, etc. So this is important because in cryptography we are assuming that the communication channel is insecure. And almost all the time this is the case, because if it is a wireless communication, it is easier to listen to the communication. But even if it is wired, you can the attacker can get in and listen to the communication. So this is why we need the encryption in the first place. So this is why we are considering lightweight encryption algorithms for the network of things. So communication channels move data between computing, sensing, and actuation. So we are using these channels between almost all of the devices we have in our networks. Since data is the blood of a nut, communication channels are the veins and arteries, as data moves to and from intermediate events at different snapshots in time. Communication channels will have a physical or virtual aspect to them or both. Protocols and associated implementations provide a virtual dimension. Wires provide a physical dimension. Communication channel data flow may be unidirectional or bidirectional. There are a number of conditions where an aggregator might query more advanced sensors or potentially recalibrate them in some way. For example, request more observations per time interval. So this is actually really important. No standardized communication channel protocol is assumed. A specific node may have multiple communication protocols between different entities. This is important because if you have multiple communication protocols, multiple encryption algorithms, and so on, this means that you need quality devices with good computational power and so on, so that they can have they can perform all of these operations. So this is the reason we are actually focusing on lightweight cryptography. Communication channels may be wireless. This is the case most of the time today. Communication channels may be an offering, service, or product from third-party vendors. Sometimes some network of things use GSM operators, for instance, as a communication channel. Communication channel trustworthiness may make sensors appear to be failing when actually the communication channel is failing. So this is also important. You have to find where the problem comes from. Sometimes the communication channel is failing. Communication channels can experience disturbances, delays, and interruptions. Redundancy can improve communication channel reliability. There may be more than one distinct communication channel between a computing primitive and a sensing primitive. Performance and availability of communication channels will greatly impact any node that has time-to-decision requirements. Security and reliability are concerns for communication channels. Obviously, this is the case, and this is why we need encryption here. Let's move on to the fourth primitive, which is eUtility, namely external utility. An eUtility is a software or hardware product or service. The current definition of eUtility is deliberately broad to allow for unforeseen future services and products. So NIST actually aims to provide subcategories in this primitive, probably in the future. But this is a very hard task, and we will see if NIST can do it sometime soon. eUtilities execute processes or feed data into the overall workflow. eUtilities could be acquired off the shelf from third parties. So of course, this is important. You will have security issues if you're getting it from third parties. eUtilities may include databases, mobile devices, miscellaneous software or hardware systems, clouds, computers, CPUs, etc. The eUtility primitive can be subdivided and probably should be decomposed to make this model less abstract. eUtilities such as clouds provide computing power that aggregators may not have. So it depends on your network of things, but if you need to perform a lot of operations, you might not have enough computing power to do them. For this reason, you may need some cloud service to perform these operations for you. A human may be viewed as an eUtility. A human is sometimes considered as a thing in public discourse related to IoT. Data supplied by an eUtility may be weighted. An eUtility may be counterfeit. Non-human eUtilities may have device IDs, which may be crucial for identification and authentication. And of course, security and reliability are concerns for eUtilities. Let's move on to the final primitive, the decision trigger. A decision trigger creates the final results needed to satisfy the purpose, specification, and requirements of a specific node. A decision trigger is conditional expression that triggers an action. A decision trigger's output can control actuators and transactions. Decision triggers abstractly define the end purpose of a node. A node may or may not control an actuator via a decision trigger. A decision may have a binary output, but there will also be situations where the output of a decision trigger is a non-discrete output. In other words, a continuum of output values. A decision trigger may have a built-in adaptation capability as the environment element changes. A decision trigger will likely have a corresponding virtual implementation, in other words, a code. A decision trigger may have a unique owner. Decision triggers may be acquired off the shelf or homegrown. Decision triggers are executed at specific times or may execute continuously as new data becomes available. Again, it depends on the network you are operating. Decision trigger results may be predictions. Analytics could be implemented within decision triggers. However, analytics could also be implemented within aggregators that are executed by eUtilities. If a decision trigger feeds data signals into an actuator, then the actuator may be considered as an eUtility if the actuator feeds data back into the node. Also, an actuator can and often should be considered as a component of the environment element. A decision trigger may feed its output back into the node, creating a feedback loop. It is fair to view a decision trigger as an if-then rule, although they will not all have this form. The workflow up to decision trigger execution may be partially parallelizable. Failure to execute decision triggers at time Tx may occur due to tardy data collection, inhibited sensors or eUtilities, inhibited communication channels, low performance aggregators, and a variety of other subsystem failure modes. Economics and cost can play a role in the quality of the decision triggers output. There may be intermediate decision triggers at any point in a node's workflow. Decision triggers act similarly to aggregators and can be viewed as a special case of aggregator. So security is a concern for decision triggers, malware or general defects. So remember the Stuxnet. Other possibilities here might be indirect manipulation of input values to the trigger by tampering with or restricting the input values. Reliability is a concern for decision triggers. Decision triggers could be inconsistent, self-contradictory, and incomplete. Understanding how bad data propagates to affect decision triggers is paramount. Failure to execute decision triggers at time Tx may have undesired consequences.